Now it's time to complete some worked examples for Chapter 1 to ensure that we understand the material we've covered. Sample Problem 1.1 reviews the scientific method. Identify each of the following as an observation, a hypothesis, an experiment, or a conclusion. During an assessment in the emergency room, a nurse writes that the patient has a resting pulse of 30 beats per minute. This is an observation. Repeated studies show that lowering sodium in the diet leads to a decrease in blood pressure. This is a conclusion. A nurse thinks that an incision from a recent surgery that is red and swollen may be infected. This is the nurse's hypothesis. Here are some further problems. Identify each of the following as an observation, a hypothesis, an experiment, or a conclusion. Drinking coffee at night keeps me awake. This is an observation. I will try drinking coffee only in the morning. This would be an experiment. If I stop drinking coffee in the afternoon, I'll be able to sleep at night. This is a hypothesis. When I drink decaffeinated coffee, I sleep better at night. This is an observation. I am going to drink only decaffeinated coffee. This would be an experiment. I sleep better at night because I stopped drinking caffeinated drinks. This is a conclusion. The next topic we covered were strategies for learning chemistry. Predict which student will obtain the best exam score. Bill, who reads the chapter 4 times, Jennifer, who reads the chapter 2 times and works all of the problems at the end of each section, Mark, who reads the chapter the night before the exam. We can conclude or predict that Jennifer, who reads the chapter 2 times and works all of the problems at the end of each section, would have the better score on the exam. Which of the following activities should you include in your study plan for learning chemistry successfully? A. Reading the chapter over and over until you think you understand it. B. Going to the professor's office hours. C. Self-testing during and after reading each section. D. Waiting to study until the night before the exam. E. Trying to work the sample problem before looking at the solution. F. Retesting on new information a few days later. B. Going to the professor's office hours may help. C. Self-testing during and after reading each section will help. E. Trying to work the sample problem before looking at the solution. And F. Retesting on new information a few days later. Well, I'd like to add that A. Reading the chapter can help. You shouldn't focus on reading it over and over, but reading it a time or two can help. Also, if you're having trouble in my class, you can access assistance at JSU for free through tutor.com, or you can reach an on-campus tutor through the Student Success Center. So be sure to make an appointment there if you're struggling. Which of the following will help you learn chemistry? Skipping review sessions, working problems as you read a section, staying up all night before an exam, reading the assignment before class, highlighting the key ideas in the text. B and D can be the best solutions. Working problems as you read a section and planning time to do that will help as well, and reading the assignment before going to class. Next, let's identify place values. A bullet found at a crime scene has a mass of 15.24 grams. What are the place values for each of the digits in the mass of the bullet? Okay, 15.24 grams. The 5 is in the ones place, the 1 is in the tens place, the 2 is in the tenths place, and the 4 is in the hundredths place. The next example is 1.573. The 1 is in the ones place, the 5 is in the tenths place, the 2 is, the 7, this is a 7, is in the hundredths place, and the 3 is in the thousandths place. Our next example is 40.5 kilograms. The 4 is in the tens place, the 0 is in the ones place, the 5 is in the tenths place. If you don't remember this, go back and watch the video. Next, we'll cover calculating a percentage. Remember, as we discussed earlier, that a percent is equal to the part in question over the whole item times 100. A bullet found at a crime scene may be used as evidence in a trial if the percentage of metals is a match to the composition of metals in a bullet from the suspect's ammunition. Sarah's analysis of the bullet showed that it contains 13.9 grams of lead, 0.3 grams of tin, and 0.9 grams of antimony. What is the percentage of each metal in the bullet? Express your answers to the ones place. The ones place would leave off any decimals. The total mass here, which would be our whole in this example, is 13.9 plus 0.3 plus 0.9, giving us 15.1 grams. Lead is 13.9 grams, that's our part, divided by the whole, which is 15.1 grams, times 100, means that our bullet is 92% lead. Antimony would be, the part that's antimony would be 0.9 grams, divided by the 15.1 gram total, times 100, means we have 6% antimony in this bullet. Tin would be 0.3 grams, divided by 15.1 grams, times 100, giving us a percentage of 2% for the tin. A bullet seized from the suspect's ammunition has a composition of lead of 11.6 grams and tin of 0.5 grams and antimony of 0.4 grams. This gives us a total of 12.5 grams. That will be our whole in our equation. Remember, percent is equal to part over whole times 100. Next, we'll calculate the percentage of lead. That is 11.6 grams. That's our part, divided by the whole of 12.5 grams times 100. This gives us a total lead content of 93%. I made some notes in the corner because I didn't have a piece of paper. Next, we'll calculate the percentage of tin. So tin is 0.5 grams divided by the whole, which is 12.5 grams, times 100, which gives us a percentage of 4% for the tin. And next we have the antimony. We can calculate the percentage as 0.4, which is our part, divided by 12.5, which is our whole, times 100, which gives us a percentage of antimony of 3%. Now, if we compare our percentages to the previous percentages, we see that this bullet doesn't match the composition of the bullet from the crime scene and probably wouldn't be allowed as evidence. Next, we'll work some problems with solving equations. We want to solve the first equation for V2. Here's our equation. P1 V1 equals P2 V2. This is a gas law equation where we have pressure times volume under the first set of conditions equals pressure times volume under the second set. These sets aren't equivalent, and therefore P1 is not equal to P2 and V1 is not equal to V2, but they are proportional. So let's solve for V2. We need to get V2 on a side by itself. In order to do that, we can divide both sides of the equation by P2. So let me change colors. So let's divide both sides of the equation, and I'll use a fraction bar to do that, by P2. Right? So now P2 divided by P2 is equal to 1. So we have 1 times V2 on the right, okay, which is just V2. And we have P1 times V1 divided by P2 on the left. We can reverse it and we can just put the V2, since these are equal, V2 is equal to P1 times V1 divided by P2. We can just put it on the other side of the equation. and put the P1 V1 over P2 on the right side. So we can just move V2 to the left and P1 times V1 over P2 to the right because they're equivalent, and so we can swap them around. Next, we're going to solve some equations for M. Our first equation is our equation for heat. Heat is equal to M, which is mass, times delta T, which is a change in temperature, times SH, which is heat capacity. We want to solve for mass here. Okay, so what do we need to do? We need to divide both sides of this equation by delta T times SH. So let me change colors. Okay, delta T divided by delta T is 1, and SH divided by SH is 1. So we have 1 times M on the right, and that gives us heat divided by delta T times SH on the left. Next, we'll use the density equation to solve for mass. D, or density, is equal to M over V, mass over volume. So if we want to get M on a side by itself, we need to multiply both sides times V. V times D is equal to M, right, divided by V times V. V divided by V is 1, so we have M is equal to V times D. We can just put the M on the left and the V times D on the right because they are equivalent. If you don't understand how to isolate these variables, go back and review fractions. Remember that 1 divided by 1, of course, is equal to 1. 4 divided by 4 is equal to 1. Any number divided by itself is equal to 1. That's the identity that we're using here by dividing V by V, and the V goes away because it's 1 times M on the right then. The other property we're using is that if we take an equality, let's say that 4 is equal to 2 times 2, correct? We know that 4 then is equal to what? 2 times 2 is equal to 4. These numbers are equivalent. Well, let's think if we had the original equation, 4 is equal to 2 times 2, and we multiply both sides of the equation by 1/4. What would we end up with? Well, we would have 4 divided by 4 on the left, which would give us 1, and 2 times 2, which is 4, divided by 4 on the right, which would give us 1. Our sides are still equivalent, and as long as that's true, it's okay. And that's why we multiply both sides by the same thing, or we divide both sides by the same thing, if we want to change and manipulate our numbers in order to isolate a variable. Next, we'll cover interpreting a graph. A nurse administers Tylenol to lower a child's fever. The graph at the right shows the body temperature of the child plotted against time. What is measured on the vertical axis? The vertical axis gives us body temperature. What is the range of values on the vertical axis? The range is going from 37 to 39, 37.0 to 39.4 specifically. What is measured on the horizontal axis? On the horizontal axis, we have time in minutes. What are the range of values on the horizontal axis? The range goes from 0 minutes to 30 minutes. Using the graph, what was the child's temperature after 15 minutes? At 15 minutes, this is our time. We can look up to the graph and we see that where time touches the graph, we can extrapolate over to the left to temperature. And it's at approximately 37.6. How many minutes elapsed for the temperature to decrease from 39.4 to 38? Okay, 39.4 is here at time 0, and 38.0 is about right here. Okay, and so that would be um, around 8 minutes. Around 8 minutes, it touches this graph on the x-axis. What was the decrease in degrees Celsius between 5 minutes and 20 minutes? So at 5 minutes, we're at about um, 38.4, and at 20 minutes, we're at 37.4. Okay, and so I would say about 1 degree C. The answer here given is 0.9, but that's pretty close. We don't have the dividers here that we need to be able to get a more exact or more precise number. Next, we'll write some numbers in scientific notation. Write each of these in scientific notation. So 3,500, 3,500. Notice that we have an implied decimal point at the end of the number. We're going to move it 3 places to the left, where it's between the 3 and the 5, behind the first significant digit. So that will be 3.5 times 10 to the third. For the next number, we have 0.000016. We need to move the decimal point to the right until it's behind the first significant digit. 1, 2, 3, 4, 5. We have 1.6 times 10 to the negative, because we're moving to the right, and we moved it 5 places, 10 to the negative 5. Next, I'll let you complete study check 1.8 on your own. Write each of these numbers in scientific notation. Pause the video and practice writing each of these numbers in scientific notation before you look at the answers. Ready? Here are the answers. If you have any questions about these problems, see your instructor.